Hi, everyone. Well, let's go on now and talk about microscopic or atomic magnetic moments. We'll see how electrons in atoms, because they carry orbital and spin angular momentum, possess magnetic moments. And then these magnetic moments add up to give atoms their own magnetic moments. Okay? Well, that's how it will work. The first thing we'll show is that the magnetic moments carried by electrons come in units called the Bohr magneton. Here, let's see how this works. Okay, so we said that electrons can carry orbital and spin angular momentum. And then since they're charged, this orbital motion of charge or spinning motion of charge is like a current loop. And so that gives rise to a magnetic moment. Okay? The simplest model of the magnetic moment carried by electrons is a semi-classical model associated with the Bohr model of the atom. And we'll take a look at that. So this is a semi-classical Bohr model. So in the Bohr model, the electron, of course, orbits the proton. There we are. Okay. Here we go. Here's the electron orbiting the proton. And it moves around in its orbit at some orbital velocity v. And of course, the orbit has a radius equal to the Bohr radius. The magnetic moment carried by the atom or the electron is equal to I times A, where I is the current carried by the electron as it circulates around in this loop. And A is the area enclosed by the loop. So clearly A is just pi r squared. And of course, the radius is the Bohr radius. So we have pi a naught squared. The current takes a little bit more thought. We can think of it this way. The current is equal to the charge times the frequency at which it goes around the atom. Okay? If it goes around 100 times per second, that's 100 elementary charges per second, which is a current. Okay? So the current is equal to the charge times the orbital velocity divided by the circumference of the orbit. Because of course, that gives the orbital frequency. Okay? So then finally, the magnetic moment is equal to pi a naught squared e times the velocity divided by 2 pi times a naught. We can cancel a few factors to simplify this. Like so. And then we can recognize something else interesting as well. Remember that in the Bohr atom, the angular momentum is quantized in units of h bar. And the angular momentum is the radius of the orbit times the velocity times the mass, okay? For a point particle moving in a circular orbit. Now, if we look at our formula here, you can see we have the radius of the orbit, a naught. We have the orbital velocity, v. We just need a factor of mass to get the angular momentum. So let's multiply and divide by the mass. Then what we're left with will be E times the angular momentum, orbital angular momentum, divided by 2m. And finally, in the Bohr atom, the angular momentum comes in units of h bar. So this is h bar E h bar over 2m. Okay? And this unit, it's like a fundamental unit of magnetic moment, because look, it's a magnetic moment, but it's just made up of fundamental constants, E, h bar, mass of the electron. This is called the Bohr magneton. And it's almost like an elementary unit of magnetic moment for electrons. Oops. Okay. And the Bohr magneton works out to the following value in SI units. It's 9.274 times 10 to the minus 24 joules per Tesla. All right.